We have one extra already.
Awesome. So just give us a second. I'll tell you when to start. We just got lunch for the team. So the other one doesn't have a good TV. You gotta try it. That's fine. Yeah.
Hey Tim, how did your final go?
Okay. I'm not too worried.
Why are you laughing?
It was pretty difficult, but
Okay.
I did what I could.
Yeah. Whatever. The year is over.
Yeah.
YOLO.
Oh,
All right, so we just so you guys know, whoever's on there, I just gave an overview for our whole team about the TRIBE program and what it is. And I know some of you guys haven't met everybody on our team, but we have an audience of about 7 or 8 people in NeuroLex watching these, and we're all kind of just reflecting on these demos, and kind of the structure is like 5 minutes pitch and 5 minutes Q&A. So I'll kind of let you guys go and cut you off at the designated times. But that being said, I'll let you go, Tim, because it's 12 and want to be punctual and on time, not get behind, and let you know when the Q&A is.
All right, sounds good. So hello. I'm Stella, and so it's a disorder that affects the substantia nigris of Parkinson's patients, and it essentially causes a range of symptoms, coordination issues, vocal changes, rigidity, and there's around 60,000 diagnoses each year. And one issue with Parkinson's is that diagnosis for it is pretty inaccurate. So based on a study done in neurology, motion specialists, non-experts, and motion experts who have been with the patient for a long time all showed accuracies of less than 85% on average. So there's a big gap on how this can be informed, or how clinical diagnosis can be informed. And one aspect that we're trying to look into is trying to use voice as a biomarker to diagnose Parkinson's. So we use the Sage Bionetwork's Empower Voice Features dataset, and using Pi Audio, the open source library, a bunch of audio features were extracted. This is not done by me, but there is zero crossing rate, energy, spectral entropy, etc. So the one that I used was MFCC, and MFCC is pretty customary to be used in audio analysis. There's the equation there, and example. There's about 400 time steps and around 13 coefficients per time step, so around 50 to 100 dimensions per patient, and there was around 58,000 unique voice samples. So I split it into 4,325 training and 481 testing. 481 testing sets, because there was a disconnect between the number of total Parkinson's patients and the number of available to be labeled. So I used a range of models. I used a deep neural network encoder architecture, a gradient boosted decision tree network, and a denoising autoencoder. So overall, our accuracies included, for me, I had 65.5% accuracy and a 79% accuracy overall, based with Vanessa, and that was a support vector machine. So look, right now, Reza and I are looking to publish. So we have the paper sort of in the works, and we're looking to submit it May 7th. So further research, we're looking to have a range of different architectures. So I'm looking to create a variational autoencoder network that would basically project whatever data that I have as an input to a Gaussian distribution in the hidden space. That would solve a lot of issues with creating, with issues of overfitting, because there's only around 5,000 samples that are labeled and 58,000 unlabeled. And that was the motivation for the autoencoder network that I created prior, which is just a dimensionality reduction method. I also am looking to create recurrent neural networks and a adversarial neural network, which is that in the center, which would both aid in dimensionality reduction and overall feature extraction. So does anyone have any questions?
Tim, very nice job. So we have a little bit of diversity in terms of background here. Can you explain to people MFCCs?
Oh, sure. So I wish I knew a little bit more about the specific mathematics behind it, but from what I understand and can gather, it's just a way of extracting spectral information from audio data. So all this was done through the Pi Audio dataset, and it's not something that I did. It was through already through the AWS offering. So
one nice way to think about MFCCs. Are people familiar with MFCCs? Mount frequency capsule coefficients. So you know, a technology like Alexa, for example, or Google Home, MFCCs is what made that marketable. They catapulted them almost 10 percentage points into an accuracy level that was usable by consumers. So that MFCCs really blew open the market for voice recognition. But it turned out obviously has applications for healthcare. It's like a 6-step high-level coefficient that you derive by doing several transforms. You do biometrics, right? It reflects multiple biometrics. If you take like Fourier transform and you put on a log scale, and then the reason it's called the Mel frequency. Mel scale transform puts it on a range of human hearing, so it actually makes the resonances line up with what you hear.
It's also rather than just filters it so that it's a human voice.
Yeah, so it's
20 hertz to 20 kilohertz is a human voice range. Each one is a different band.
And at the end of this nice little complicated formula, you can see the log is in there, and then there's the Fourier transform in there. You can get basically 26 coefficients, but the lower coefficients end up actually correlating with the structure of your voice box. So it actually reflects your biology. You can actually draw some parallels there. So depending on the structure of your vocal cords, that would be reflected, so the lower frequencies, but the higher coefficients will reflect more of the sort of higher range pitches you can achieve. Anyways, there are some parallels. People have done some work actually to explain it more than just a math symbol. So that's what Tim used here.
Nature trickling. Tim, I had a question. So on the adversarial network that you're planning in the future, can you briefly describe like the generator, I guess, and the discriminator, the network structure of that you're thinking about?
Could you say that again, please? Sorry,
can you hear me? So I was just saying, could you briefly explain like the adversarial network architecture that you're thinking about doing in the future?
So here's just sort of the layout. So the concept of an adversarial network is you have two separate networks that work in tandem, and the input of the layer. So just sort of a general autoencoder would have a bottleneck dimension shown here that encodes all the information. So you have a encoder architecture and then a decoder architecture.
Yep.
And this is useful and it can reduce the dimension of the data, but it has issues creating a way of specifically mapping it to a useful dimension. So these specific dots might not represent anything useful. So if you were to create an adversarial or a variational autoencoder network, then you would be able to use these latent layers as useful information. So you could have another what is this? Yeah. So this architecture would be able to, use the information from the layers and.
So the discriminator would be the mean value from a Gaussian distribution, like to figure out from there.
Yeah. So that would be true for variational autoencoder, I think.
Okay. Yeah, I was just curious about that.
Yeah, and then our adversarial would be you just have a separate network that is able to figure out like whether or not the latent vector that you output is useful.
Okay.
Yeah, that's
cool.
what that is.
Very cool.
Any other questions?
Yeah, you guys have any?
Where did you get your spoken data and like your modeling from?
Oh, this is okay. Yeah.
Could someone repeat the question? Sorry.
I think I was asking about where the data came from. It was from actually Sage Bionetworks. In 2015, they launched an open app on the App Store. About 10,000 people participated. It was really successful. And part of that was 10 seconds to say so one syllable.
I was like the Emory stuff that we, okay.
Yeah. Yeah.
Using so right now.
The only thing the question I have is, what other knowledge-based techniques are out there that this is kind of competing with as a solution? How will you, now that you've seen some results, you feel competing in practice?
Tim is just asking about what other techniques exist for diagnosing Parkinson's and how this fits into that ecosystem.
Oh, sure. So recently, Ben Pittman, he's also a member of the data science team at UW, and he just created, using the same data set, but a different aspect of it. He used the, I think it was the gravity and accelerometer data from a iPhone to diagnose Parkinson's. So that's another non-invasive biomarker usage. Other ways are usually just you have an expert system or just some specialist that comes in and diagnoses the Parkinson's based on the range of symptoms like aggregation, vocal changes, and rigidity.
All right, I'm going to move on. I'm going to move on because we were kind of low on time. Thanks, Tim. That was great.
Thank you.
Yeah. All right. All right, Larry, I'm going to put you up next. Let me allow. Sorry. I just let you, Larry, share your screen. Can you share your screen now?
I think Tim has to unshare before I can share.
Let me see. See if I can unshare. Tim, is there a way for you to transfer the screen? Actually, here, no. There, you should be able to share now.
Okay, yeah, it works.
Okay, okay. And Tim, can you just disable sharing your screen? I think that's what we got to do. Yeah, I can't control that. Let me see. Yeah. Okay, cool. I don't know if you can stop the share. I might just kick him out. I could also do that. Okay, there we go. We're good. We're good. Never mind. Awesome. All right, there you go. Ahead.
We're all here. Screen and everything.
Yep. We can see it.
Okay. So the demo I'm proposing is the optimized data science pipeline for mental health illnesses. The reason behind this was I noticed that it would be a lot easier to train models over time if there was like a standardized way to really just pre-process data, accumulate data, separate data in any way, and then building pipelines on top of it, and generalizing them to say like depending like if there were like neural networks or support vector machines, logistic regression, just having the pipelines be generalized so that it can essentially like work on any type of data, any data set. So I wanted to also be able to speed up the development of models, which inspired me to like pursue this pipeline on top of any sort of biomarker data. So like as before has been said, like important biomarker data has been voice, accelerometer data. There's any variety of applications in terms of biomarkers. And there's still many biomarkers that are being verified to this point. And I've also been working on standardizing feature embeddings, which I'll go into a little bit in the next few slides. And then for my purpose, I tested my pipeline on bipolar data set from YouTube because it's my primary research interest. So the features I'm looking at are the Google Audio set, the MRMR feature extraction, and the GMAPs. These are all different feature embeddings that we can create. So GMAPs and MRMR are two different ways to extract data that have been standardized either by industry or they have been, or not industry, by research. And the Google Audio set is a way to extract data that Google has provided, where you can get embeddings based on each second of the audio. The pipeline goes into data extraction, data cleaning, and models. For what I have right now, I have the audio set embedding working, and I have some data cleaning going on. And I have them SVM and neural network models set. And I'm planning to add more natural language processing models into the pipeline. So my results on the bipolar data set, there was about 80 to 90% accuracy comparing for the neutral state. So when the participant who has been diagnosed with bipolar disorder is more in a stable state versus like in a bipolar state, which would be either manic or depressive. But I observed that it obtained a low F score, and I noticed that because it was a high false positive. So in this case, if I were to continue with the YouTube data, I would have to collect additional audio samples for the neutral state, because I noticed that there's significantly higher amounts of manic and depressive states rather than the neutral state. And then as a metric of like how the pipeline works, the code is fairly easy to follow. Setting up a pipeline only took like 5 lines of code. So I thought that was very easy, very quick to use. Aside from like I had the design choice that if someone wanted to use the pipeline, they would have to do the labels themselves, the code for the labels. So for the growth beyond the project, I'm hoping to gain further experience from building the pipeline and learning about the data science models. And I've gained an understanding of posing research questions. And we've got to address the domain of the research that actually has an effect on my own life. And for future work, I want to be able to pursue speaker diarization, which is like just essentially separating who is who in who is speaking in an audio sample. And I want to continue the MRMR and GMAPs embeddings. And I want to continue to do work on the digital biomarkers and expand the selection data we can put, use models on. And yeah, I plan on pursuing future research with Reza. I want to become a tribe mentor, hopefully, and then I want to continue this pipeline.
Thanks, Larry. That was awesome.
Nice work.
I think you guys have any questions, let you guys go.
And this is just all these presentations are kind of brainstorming about a bunch of different things. And what I was thinking now, and kind of be after both projects so far, is have you seen any research combining kind of audio features with features from other research? So we talked about like the data with the iPhones we're collecting. Like, is there any way we can combine the features across different types of data?
Can you repeat that question? Sorry.
Yeah, so for future work, is it possible to kind of run some of the same models, but instead of just looking at audio features, can we combine the audio features with other types of features outside of audio, other biometric data, or
like walking,
Like Fitbits or whatever.
Oh yeah, I think I understand the question. Yes, it is possible to run them in joint. That of course is actually I think that'd be more of an engineering choice, and then that could expand upon the design of a pipeline. So it's definitely possible, but it also should have like there should be some way to map that, like say like iPhone data, I say like accelerometer data, to like the respective speech data. Or if we're just isolating the speech, or I mean accelerometer data from the iPhone, then that could just be a model on its own, and it should be able to model the pipeline. And by the pipeline.
I think a good idea, like for this, originally it was stress detection for me. Like I was working on a stress algorithm, and heart rate variability could be the output model for severity of stress. So the input would be speech, the output would be heart rate variability. And if you could train a speech model on heart rate variability, objectively defined as a heart rate variability from an iPhone watch, then that could help us estimate heart rate variability from the voice alone. Sure. And that's the stuff that I was interested in before, but I agree with you, like adding a more rich feature embedding to it could add to accuracy.
Yeah. And there are some really academically also the previous director of NIH comments. So he joined Google Verily and ran their mental health division for a couple of years. Now he's at a startup called Mindstrong. And they're the ones that have been in the space the most. And they're doing things like typing speed, cognitive processing speed, based on how fast you search on your keyboard on your iPhone to reflect, if you're depressed or not, or that kind of thing. So people are doing it.
Cool. Well, we'll move on. So just hit 12:20. So we'll get to Audrey. Are you up, Audrey?
Nice job, Larry.
Yeah, great. Oh, yeah, give it that.
Yeah, Larry. Totally unbiased advice for me.
I'm happy about that.
Okay, I'm just gonna share my screen real quick then.
Yep.
Okay.
Cool.
Did that go through?
Yeah.
I haven't done this before, so. Okay. Oops. My computer's laggy. Just get a presentation.
No worries.
All right. I'll start the conclusion.
No worries. I love the presentation.
Okay.
I'm excited about this one.
So I had completed a research demo and on utilizing voice analysis to diagnose early stage glioblastoma multiforme, or GBM, so brain cancer. So as a problem, as a disease, it is the most common, most aggressive, malignant, and lethal primary brain tumor, with survival rates only at about 1.5 years after diagnosis with treatment, and is also the most costly cancer just based on the diagnostic and treatment expenses and the cost to society. So treatments often involve surgical intervention. TMZ is one of the more common, more recently discovered treatment methods, as well as radiation therapies. And this treatment regimen only increases the 2-year and survival rates to about 27% and 11% respectively. So it remains incurable and still tends to relapse in the same area where it developed. And it's often too late in the cancer's biological course to successfully intervene and treat the cancer. As well as these tumor cells tend to migrate, so it makes targeted therapy much more difficult. So common symptoms that we would be of interest in analyzing just based on like voice samples and syntax would be decreased cognition, mood changes, memory loss, and of course speech and language difficulties based on where that tumor is located. So it perhaps may be located to the frontal, temporal, or just multiple lobes that do compromise linguistic function. So some areas that perhaps if there were some very localized tumors would be Brodmann's areas 39, 40, 45, and the superior temporal gyrus. And so current diagnostic methods are neuropsychological exams, neuroimaging, so structural MRIs and fMRIs. And using spectroscopy, you can actually enhance the dynamic contrast to about 87% accurate with spectroscopy and structural MRI diagnostics. And surgery, of course, is always used often with biopsy and resection, but this is, of course, very invasive and time-consuming and costly. So the impact of voice analysis instead on early diagnostics. So currently brain cancer ranks 4th in cost per month, which reaches about $8,478, about $8,500 per month, which accounts for the radiation therapy, surgery, and indirect costs based on, say, like lost wages because you can't work. So the median monthly out-of-pocket is about $1,300, and the serial MRI to monitor the progress of the cancer is about $500 to $3,000 per scan. So this is very costly to both the patient and the medical facility that is doing the diagnosis. So we can prevent the above expenditure that I've shown for the patients and these facilities just with early GBM detection and diagnosis with, say, your PCP. So if you went to the doctor's office, did a quick voice test, and then they ran the sample through to detect any features that may be suggesting that this person may be prone or has a brain tumor, glioblastoma, then they could go get a CT scan and kind of ensure that this is the correct diagnosis, and then you can treat this early on, much earlier than you may after the symptoms have already been prominent and it's too late to actually successfully treat. So we would improve recovery rates and outcomes with this early intervention, and this would allow for the treatment of the tumors without surgery and potentially before the tumor migrates. So the goals of my demo, when I had done my research, there were no clinical trials listed, no competing patents, no literature, and no early stage diagnostic within the FDA website when I looked this up in about January for voice diagnostics of GBM. And with my demo, at least, I hope to develop a basis for voice analysis and diagnostics, and hopefully develop this into some sort of FDA submission in the future upon further research and optimizing a model. But my goal specifically within these last few months was to develop a preliminary model for early diagnostics by just extracting features from the YouTube voice samples, because these were most readily available to me from GBM patients and survivors. So the reimbursement plan, I'm not very well versed in this area, but I've done some research into the ICD-10 code, and this is the one that would be most relevant, although we did not have any digital screening reimbursement plans outlined, so this would be a new code to be pursued in the future if this were to become some sort of PCP test. But based on the preliminary results, I did link the YouTube data spreadsheet with the 20-second clips are what I used. And actually with Jim's help, I had these sent over to him, and he was able to run Python and extract the features for me. But I had about 21 samples collected. I formatted a new template for this YouTube data extraction, just a basic Excel sheet. But each sample was about 20 seconds roughly of just that patient talking. So I had to go through the video and make sure that it was just them speaking. And I've yet to do further analysis for different features. But this was just based on any features based within their diagnosis, based on the basis that they were diagnosed with GBM. And so the summary of the models is also linked here. But with the accuracy, the logistic regression of both the audio features and text features, after I had transcribed the same clips, was about 83. So before doing the text features, I believe this is actually from one of Jim's presentations for the meetings, but it was a 73% accurate model without the text feature analysis. So there's a very strong basis that this could be developed with more sample size, with a larger sample size, to be more accurate. But the future directions that I plan to carry out would be to enhance and optimize the current text-based and audio feature models. So that could be using more an increased sample size of YouTube data, or potentially if I was able to go into a clinical setting, say like Hillman Cancer Center here in Pittsburgh, with IRB approval to gather local patient samples. And then I hope to extract additional features such as based on sex, the stage of GBM, so early or late stage, say like 1 and 2 versus 3 and 4, or the glioma type and location. And then compare these against controls, of course. And then just my personal goals, I'll be finishing up in Pitt next year to pursue hopefully my master's in clinical research and an MD. And then I hope to maintain my project involvement and extend the scope of this current one, but as well as enhance my computer science skill set that is not very well developed yet, so I can hopefully run some of these analyses on my own. And I'd like to serve as a future mentor for fellows. But I just want to say thank you for providing me with this opportunity. I haven't really had the chance to do an independent project like this yet, but I just want to say thank you for all your help.
Thanks, Audrey. You're a rock star. Thanks so much. I'll let you guys have any questions. I've been working with Audrey on this for a while.
That's right. I'm curious about all the what else can we do or explain about it. And one I was just curious in the research, and I'm definitely far from being a neurobiologist, but is it even possible to predict this type of tumor before it happens? Is that even a possibility? Maybe not just in audio, but
Is there any speech cues?
It's never been
I mean, I would hope that there would be some sort. I've only been analyzing, or at least like looking into the features for those that have already been diagnosed. But hopefully, there are some ways that the individuals that had been diagnosed. I'm assuming that biomarkers are actually currently the ones that are being, like molecular biomarkers are currently being explored with that. I'm not sure that right now we could, assuming that we even develop a model right now that's accurate enough to diagnose like in its form. I'm assuming in the future there's some way to do that. I just haven't considered that.
Right, and that can be a way to get data. There isn't really
and we're kind of working our way backward there as a community, starting from exist to the.
It's like, this is tough too. Wherever. Maybe your brain is already yeah. So you have to rely on something else.
But it's not that means this specific tumor in this location. And the high level thing I was thinking across all these projects, and just thinking big picture, imagine having like a filter on your phone that you install an app that listens to all your audio and it can give you like monthly or daily reports on potential diseases and issues you may have with your body. Really incredible. It's something of like the
Sounds like a constant nightmare. Emails.
I'm hoping that with having some sort of features for the early stage glioblastoma, that you'll be able to extract some features before the cancer is actually prominent, but that's another future step.
All right, we're going to move on. Audrey, thanks so much.
Thank you.
It's been absolutely and yeah, we totally will follow up on you getting more computer science skills.
All right, sounds good.
If we can help, let us know.
What are you majoring in?
Neuroscience.
All right, so the next person up, me. So, let's see. So Dylan, are you there, Dylan?
Yes, I am.
Okay. Hey,
everyone.
Yeah, I don't know if you can see us, but yeah, thanks. We've been getting a lot of University of Pittsburgh people, by the way. Audrey's from the University of Pittsburgh, Dylan's from the University of Pittsburgh, and also Tim is from the University of Pittsburgh. So you guys have been delivering on your demos. But I'll let you go. Do you have a screen share?
Desktop one.
All right, cool. Awesome. All right, we'll go on mute. Yeah, you take it from here.
Okay. Just want to get this out of the way. Okay. All right. So before I start, I just would like to say thank you, NeuroLex, for this opportunity. And thank you, everyone else, for listening, for your attention. Hopefully, you can learn a little bit more about me, and as I've learned a little bit more about you. So without further ado, I'd like to talk about the detection of early stage psychotic disorder using voice analysis. Oh, that was supposed to switch. Okay. All right. Psychosis is a severe mental disease that affects how a person thinks, feels, and behaves. There's an estimated prevalence rate of 1%. However, it's most likely higher as many go misdiagnosed and just undiagnosed altogether. This is a disease that affects all socioeconomic classes, and society places negative stigma on this disease. It's believed that a lot of patients are violent and reckless, but it's really not the case for vast majority. The cost of diagnosis can be up to 15,000 over 5 years. This includes many unnecessary tests, such as blood tests, urine tests, echocardiograms, that ultimately play minimal role in diagnosis. Some of the patients that whose data I used in this project mentioned that their bills were over 20,000 over just a few years span. So it's very costly. And ultimately, overall, there's a lack of a clearly established objective biomarker for schizophrenia. So for my project, I used audio samples collected from YouTube. These were 20-second segments of either schizophrenia patients or controls, just anyone else really, and speaking in emotionally neutral free speech. And mainly schizophrenia data was from vlogs or interviews, and control data was from professional athletes' interviews. There are two groups, schizophrenia group and control group, relatively equal male to female ratio. Ages varied from adolescent to middle-aged. I focused more on adolescent because thought it'd be more important, as this is the time when the disease starts to form. So, and I just wanted to extract the audio data and run the raw voice data through several types of SVM models, which were the ones that NeuroLex uses. So I got my audio data to Jim, and he put it through a variety of different tests. As you can see here, I displayed the 4 different models that had the best outcomes. As you can see, text-only feature set was most accurate in all models, and the random forest and hard voting models were also the most accurate at around 79%. This data actually lines up with published data from Guillermo Cecchi and colleagues. And so I'm not going to speak too much about the models because frankly, I don't know, I don't understand them very much. I am not a data science person, and so I can't speak too much about that, but however, I can speak about the text-only feature being most prevalent. So the fruits of my project. The results, I believe, seem to exemplify the enormous potential for AI and machine learning based diagnosis in psychosis, psychotic disorder. My sample size was very low. It was only 30 controls compared to, it might have been 30 schizophrenia data points, or I'm not sure if, Jim, if you added any more of your own.
Yeah, a little bit. It was like 50 total, but and I mixed it, so it was adolescents and adults. So, but yeah, in general, it was about 30 for adolescent.
Okay. Yeah, so however, I chose each sample with great care to see, to try to make sure each one was emotionally neutral as possible, and to make sure that they weren't segments, they were full sentences. So I believe, as shown in the previous slide, the text-only feature set was more successful. This could provide insight to the importance of linguistic variables as opposed to audio variables such as vocal pitch and rate of speech in diagnosing schizophrenia. I'd also, for me, just provided insight into the perspectives of these schizophrenia patients who I observed. I learned how they wish to be treated. You know, it could help to reduce the stigma, which I feel strongly about. Learned about their day-to-day life, and also, as previously mentioned, some of them mentioned their first psychotic break and detailed their cost and distress that was associated with it. Overall, YouTube is a reliable medium for obtaining voice data for schizophrenia patients. There's new videos really being posted all the time, and weekly vlog. Many of them have weekly vlogs, and actually a lot of them interact with people that comment on their videos. So a little bit of encouragement could really, lead to positive outcomes for them to continue their vlog and want to help ultimately in a project such as this, just to provide more data. And also one thing that I noticed was that a lot of these videos from schizophrenia patients were taken in the morning. A lot of them mentioned that it was morning when they took the video. So this could possibly provide insight into when the patients are feeling the least stressed, and it could possibly have ties into stress levels. My personal goals, I'm graduating tomorrow. After this, I hope to secure a research assistant position and continue studying the dopamine system's involvement in schizophrenia. I've been doing this for 2 years now at Pitt, and I really think that it's my passion. Eventually, I wish to apply to grad school for neuroscience. However, I think that's years down the line for me. Also, I'd like to continue my project and involvement with NeuroLex. After graduation, when I have more time, I'd like to self-learn coding languages and apply this knowledge to machine learning models to familiarize myself with how these are made and structured, and hopefully I can get more data and look forward to publishing a paper. Also, I think I could use the $500 reward from this to fund a trip to the Stanford BioX Brain Connectivity Workshop this June, because many of the lectures there, well, one in particular I know is going to be related to cognitive changes in psychiatric disorders, which I'm really interested in about, and I think it could tie into NeuroLex. And I'd just like to, let's see, what time is it? Just like to talk a little bit about what I learned from NeuroLex, this experience. I learned that research is global. It's happening all around the world. The opportunity to work with tribe members from around the world working towards this single goal has been really meaningful to me. And it provides a larger perspective of how this could affect have like a global effect. Also, this was my first involvement with non-university research, so I learned that research kind of can move as fast as the research drives it, and if I had more time this semester, I think I could have gotten a lot more data and produced a more hearty project. And also just to think, I think I've learned to think about the impact of biomedical research from many perspectives. To me, this means perspective of the patient, their family, doctors, and society as a whole, in order to just create the most beneficial product as possible. Yeah, that's it.
Awesome. Dylan, you like absolutely great job, and thanks so much for all your hard work. And obviously, this is something very personal, motivating for myself with my brother, his condition with schizophrenia. It's always great to see and have empathy for these patients. But yeah, I'll leave it up to everyone else to ask questions. I've known Dylan's project for a while. I think he's doing some great work in his lab that he's been able to bounce ideas off of with us.
Excellent. One question I have, you did mention that we partnered with two models to yes, seriously, any kind of challenges or hypothesis about audio?
I can't hear what you're saying. I'm sorry.
Okay.
I apologize. I'm also going to be talking fast. So one question I had around the model is a little bit. Is it better? Can you hear me? Can you hear me better?
A little bit better, not much more clearly. Could you translate, Jim?
We're talking directly into it. Yeah. One question I had to the model. So the video is can you hear me better now?
It's really quiet. It's really quiet.
It's really quiet. Is it calling from somewhere else?
Jen, see if everyone else is muted. It's picking up noise.
Can you hear better now?
I can hear you perfectly.
I think it's just the direct. Sorry.
Good. Speak up.
Yeah, so I could just talk a little louder. But I was curious with the models. Because like kind of our hypothesis that audio is richer data, yet in this case it is having a lower accuracy, and in some cases a significantly lower accuracy. So is it that we just have less audio features and more text features, or what do you think is contributing to the accuracy difference between audio and text?
Well, I think during this whole process, I've actually been doing a literature review to find different aspects and parameters of speech that most highly correlate with schizophrenia. And I've found that what seems to be most important is linguistic, syntax, and semantics, as well as temporal parameters of speech, so pauses and interjections. And what seems to be least important actually is like the rate of speech and the like the pitch and
I can add on to that too. So my brother, he speaks in very disorganized sentences when he's psychotic. So they'll tend to use new words that don't exist. And he also will have very disorganized structure and repeat words back the same word over and over again. And so the features that just generally seem to work for this disease are linguistic, like you were saying, and it seems like all the published papers support that.
Okay.
So the audio is less important.
Interesting.
It's more the text.
I think one of the things that we're discovering is that we've last night is that audio is kind of like the first step to getting language features, linguistic features. And in some situations, we'll find that the linguistic features are getting less accurate results. The audio features are getting better, which we found with some things like intersection.
It depends on the problem.
Depends on the problem. And so, but the first step is get the audio, and we can derive linguistic features from the audio.
I have one question.
Yep, I'll repeat it back.
So why is it important to have the neutral emotional state?
So the question was, why is it important to have a neutral biological state?
Neutral emotional.
A neutral emotional state. Sorry.
Yeah, I'm not sure. So when I talk about neutral emotional state, that's the way that the person is speaking to the recorder, whatever is recording them. So I imagined, with this, the end goal of a device to diagnose diseases with voice, like it would be most useful to have the person read possibly an emotionally neutral piece, so that it doesn't affect their affect, and so whatever kind of affect they're feeling right now, or kind of emotions, what gets analyzed, and so in some other studies, I believe they've made sure to use emotional text so that they can prevent this variable.
All right. Yeah, sounds good. Well, we'll end it now with Dylan. Thanks so much. We're gonna take a quick break and be back in 10 minutes or so. The next
videos or
no, there's some more pitches and then there's my last two videos.
okay.
Thank you so much. Okay, cool. Well, go ahead. You have the floor. I'll mute us, and we're excited about depression. Not really, but time to be.
Okay, so hey guys, my name is Wendy, and I'm doing depression, I guess. So, as you guys all well know, the depression is one of the most prevalent mental disorders in the United States, and more than 3 million people are diagnosed with depression in the world. And it seems pretty obvious, but depression and suicides are linked, and an estimate of about 60% of those who do commit suicide, successfully, are depressed. But of course, not all depressed people do commit suicide. They say it's only 2% of depressed patients actually commit suicide. But in any case, suicide is the 10th leading cause of death in the United States. Currently, the way it's diagnosed is pretty slow and inefficient. So there's two ways where how it's diagnosed with the way it is now. So one of them is physicians, pretty much, so the psychiatrists. But the disadvantage of that is that it's pretty much symptom-based and it's very highly subjective, and it's really hard to standardize the disease. And there's a very high chance of misdiagnosis because depression and anxiety have similar symptoms. And the other way that it is diagnosed is through self-assessments. But the problem with that is it's essentially inherently flawed. flawed because patients do have to honestly and critically assess their own behavior, and sometimes like even they think they are, it may not necessarily be the truth. So the solution that I'm proposing is essentially use common vocal traits known in depressed patients, use that as a baseline, and then use audio biomarkers to quantitatively diagnose depression and its subtypes. There are two acoustic features that I've been looking at. It's MEL frequency, MFCC, and GSS. That's like those two were the main ones in like all most of the papers I had been looking at. So MFCC, which is MEL frequency cepstral coefficient, is basically short-term power spectrum of sounds. It's based on a linear cosine transform of a log power spectrum, and essentially allows to scale the pitches to produce equal pitch increments, and then GSS is the inverse matrix of the glottal frequency values. And essentially, like looking at these papers, they all kind of said it's around like it produced around an 83.9% accuracy in differentiating between depressive patients versus non-depressive patients. Yeah, so it's pretty accurate. Like at least you're able to quantitatively diagnose depression. And these were just like 4 of the videos I've been looking at. Basically, what I've noticed was there was like monotony and a lot of slurs in these patients. It seems pretty standard that all these patients like just like they kind of have like a monotonous voice. It's like there's not much variation in pitches in the patients. But obviously there needs to be more research on doing analyzing all these patients and creating a good baseline in like a future app or wherever later. So the impact of this is we can diagnose patients like more accurately and rapidly with less subjectivity, like on either the patient side or the physician side. And also because a lot of people don't like going to a doctor or admitting that they are mentally ill, or if they think they're fine even though they're not, and they don't want to be medicated. So like having this will allow like friends and family to be able to diagnose the patient and know if their family member is maybe depressed earlier, so and perhaps decrease the stigma of having to see a physician or having to be medicated. So so it'll allow them to be more aware earlier, which is essential on the patient's part. And this will also allow like again to track quantitatively track psychiatric treatment, because right now it's pretty much qualitative and again very highly subjective. And hopefully in the future we can combine this with video so we can actually track facial expressions of depressed patients, so we can increase the accuracy of what's going like of the treatment and of diagnosis. So my next steps are so I've actually started a medical device company with a few members of my senior design group. So we're a group of 6, and we officially got together in October or late October, November, and we actually officially incorporated in February. So our first product is a rapid priming syringe, and we actually have a provisional patent application already submitted. Currently, we are still in our prototyping stage, but we're hopefully going to be getting our not proof of concept, but our in-lab testing prototype, like by the end of next week, so we can start doing in-lab testing. And we're also entering 4 additional venture competitions. So we actually earlier this month we participated in Texas Christian University TCU's Values and Ventures competition, and we won 2nd place in the elevator pitch track of the competition. So yay, that was really stressful. And we're currently finalists in UCI's new venture competition, but we won't be able to know anything about that until next month, because that we'll be doing the pitch part of the competition then. And of course, I would love to mentor future tribe members later and participate in NeuroLex.
Thanks, Wendy. Thanks, Wendy. This is awesome.
Yeah.
Thank you, Wendy. Will you post that paper, the Tamaguchi paper, on Slack?
All right.
You have that Tamaguchi paper from 2018 you mentioned about depression. Will you post that on Slack?
Yeah.
Sure. Thank you.
Yeah, no problem.
Curious about that.
Yeah, because we haven't seen that paper. It'd be cool to look at it. I guess, do you guys have any other major questions? I guess the only status is sorry that we didn't get you a lot of data for depression. We're working on a pilot now with Mental Health America that is kind of being collected. We have about 500 samples or so in that already. And so if you want to get more active involved in the depression pipeline, we have some stuff going on as well.
That's cool.
So love to keep you engaged after if you want to be involved.
That sounds really cool. So this past 3 months have just been absolutely crazy with school and the company. Literally for the next 45 days, I have deadlines back to back to back.
Oh wow. No worries. But thanks so much. We gotta move on to the time. But
Okay.
We'll post on Slack.
Well, thank you if we have other questions.
Thank you, Wendy.
Awesome. Very good.
There's a chat sharing too.
You can check the chat. You can ask her in the chat. All right. So the next person presenting. You guys have it up. Is Hannah Gersh. I don't know if she's going to be here today. We'll see. We'll move on if she's not in the room. And then Allison, are you there?
Yeah, I'm here.
Do you want to go right now? Because Hannah might join us later, or she might have done a pre-recording. I'll look in the.
Sure. Yeah, I can go now if that's most convenient with the order.
Yep, that'll work great.
Okay, let me go ahead and share screens then.
Okay.
All right.
Where are you, Allison?
San Francisco Bay Area. Okay, are you guys seeing my screen right now?
Yep, we can see it.
Go for it.
Okay, perfect. So I'm Allison, and today I'll be presenting using voice analysis to diagnose common colds. So as someone who wants to go into primary care, I really wanted to do this issue for a lot of reasons. So for one, common colds are the most frequent acute illnesses in the US. The estimated cost of a primary care physician visit is pretty substantial. And then estimated time to get to primary care facilities based on a study in Washington is also a pretty big number. And generally, there's also shortages in primary care physicians and providers overall because of how frequently they are visited as physicians. And so all of these cumulatively leads to a need to diagnose common colds more effectively and efficiently. So goals for our demo, twofold. So on one hand, I wanted to start data collection for normal versus common cold voice samples, and then ultimately run those through some kind of software script to create a trained classifier that would distinguish between healthy voice samples and common cold samples. And so to address each of these, for data collection, I turned to YouTube for voice samples. mostly because I recently graduated in December from my undergrad, and so it was a little bit more difficult to get affiliation with a hospital setting. So this is like the best way for me to get my data that I needed to do the analysis. And then in terms of software and scripts, used two main sources. So yscrape.py was a script that my mentor gave me to feed in to get some WAV files, and then use Pi audio analysis for the analytical part. In terms of data collection, so ultimately the first goal was to get WAV files to feed into Pi audio analysis. So I made two different spreadsheets, one cold and one control. So for these, I wanted to keep them related. So I turned to files of people who had colds and then try to find the same person's video where they weren't sick anymore to keep those as the control files. Fed those into yscript.py and then got out 20-second WAV files on my local that I could feed into Pi audio analysis. And so for these, two different things came out. So first, I would use train classifier to create the SVM classifier files. And then I pulled out like a set of 12 different voice samples to run on classify file to see how effective they were. And so preliminary results I had. So in total, I fed 38 healthy files and 44 cold files. And then just like a brief overview of what this table shows. So for instance, if I fed in a female adolescent who had a cold, which is like the second column for each of the Y and the X, it says 91%. Pretty much what that means is that it basically outputted that it was most likely 91% cold and then 9% control. And I did that for each of 12 different files to see whether or not they were effective. And for the most part, right now it's just preliminary. So anything over 50% I categorize as green as correct classification. And then I went on just to wanted to look at more different results with different factors. And so I also looked at age and also gender to see whether or not they would be effective in those ways. I think they weren't nearly as accurate as categorizing all of them together. And I think most likely that was probably because of the number of files that I ended up putting in, because the more I split it off, the fewer files I had for each individual area. So obviously the fewer number of files, the less accurate the train classifier would be. And so I think some further steps I would take at this point. At one point, I would want to analyze the confusion matrices from building each classifier, because I have those saved in files right now. I think that would be a more overall better way to analyze whether or not they're effective, rather than feeding in specific files and having that uncertainty with there. And then I would also want to turn to look at other environmental factors, like whether or not the video is outdoors or indoors, maybe nationality of voice, and also definitely noise in the background of videos, because that's definitely the biggest issue I see with taking YouTube files. And then in terms of impact, one of the earliest symptoms of a cold is a sore throat. And I think that's the reason why voice analysis is really effective for common colds. And then ultimately, I'm hoping that this would allow patients to self-diagnose their own conditions and help them take preventative measures before their illness becomes more serious. And all of these ultimately, the goals would be to reduce patient-physician interaction time, which obviously we want to see our primary care physicians, but also there's limitations with how often that people can feasibly take time out of their day to go see them. So this is all just a way to make people's lives easier on both ends. And then for me personally, goals, so I start medical school later this fall. And so my career goal is to be primary care physician by day, and then probably try to do some research or innovate definitely a little bit when I'm not seeing patients. And so on one hand, I definitely want to move data collection to a hospital primary care setting, or any kind of clinical setting where we could have actual patients participate in a real study to keep data collection more structured and more reliable. And then I think for me, because I want to be in family medicine, I also want to, through medical school, learn about other areas of primary care where this could be applied to, and see what kind of diagnostic exams we could contribute to other diseases. I think the next step probably would be to look at cold versus flu or other kinds of similar illnesses that people can't quite determine on their own. And then one thing I talked with Jim about was possibly starting to draft a grant proposal to Minute Clinics for CVS, just to see whether or not other areas would be open to collaborating with us to start a pilot study based on this simple proof of concept that I've demonstrated. And then also, I guess more socially, when undergrad, I was a tech major on a pre-med track, and I think it wasn't as common when I went to school, but now I think I see more younger students wanting to go down this track. And I think it's a really relevant area to be in these days. So I probably want to continue to be a mentor for future people who are interested in going into medicine, but also wanting to do some cool research in this area. So I want to keep on staying involved that way. And yeah, that's pretty much it.
Awesome. Thanks so much, Allison. This super exciting project. I think colds are like an area we've had a few conversations with internally. And I remember when I was sick at the Texas Medical Center at TMCX in Houston, I started recording my voice, and it was like scratchy, cold background in my throat, and I was doing a lot of self-quantification. And it's cool to see like this being applied. And, totally can extend it to larger areas, Midclinic being one like you mentioned, or other pilots. And I know Reza has some reach into primary care within UW as well, but we haven't really talked deeply with them yet in this area. So might be another area. But you guys have any other questions?
Yeah, I thought that was great. From an audio spectral analysis, it was kind of mid to low frequencies, the way the voice, when you do have a cold, the way it's almost kind of like the rate of oscillation can be detected pretty easily. I'm really fascinated by this subject as well, and trying to hone in on that. And actually, I think with relatively a few hundred samples, maybe we can hone in on where those are, and because when you have that scratchiness in the world of audio, it has a look to it.
Yeah. Yep.
So cool.
Yeah. The other question that I have is kind of thinking about, putting this to market. Of course, you're owners thinking from the product side and one side of the business. Like, how do you envision seeing this like being used kind of in more practical day-to-day sense?
Yeah, I think there's definitely a couple of ways. I think on one hand, we could move them to like a more medical driven setting. So I guess for me, like I definitely in the future personally want to be like a person in between to navigate between doctors who might not know that much about how technology can be used in medicine, and also for people who don't know how they can make their lives easier with technology on like the patient side. So I think if we move it to like a hospital setting, I guess that might be a cool way to triage also, like, having people first give a voice sample and, determining that, I guess, more quickly than physicians having to like come in and see patients and make diagnoses based on those results. And they can just kind of analyze them together when they're like seeing each other and make that more efficient. And I think on the other side, like you could also market that just to, I guess, consumers and not people in medicine, and also just make their lives easier if they know that, oh, if I'm not sick, then maybe I don't want to go and see a physician. Maybe it's just like a bad day or something. So I think it could be marketed in a ton of different ways. And it kind of depends on ultimately like how much people in medicine want to get involved with this program, because obviously it affects them a lot. So yeah, just a couple of things I was thinking about.
Yeah, it could be interesting to kind of find a way to pilot this at a facility somewhere. Imagine us having like a little NeuroLex like stand or something. You go up and talk to it and fill out a survey, and you can say, I have a cold, or I think I have a cold, or I don't. Yeah, while they're in the waiting room, maybe they can get some kind of analysis while they're waiting on the doctors.
I think with the right research too, the more towards the end, you need to have an app that works with voice and also with the camera. That has the model, so it can take the audio, voice audio, and the visual on the throat. And with machine learning, they come out with some things that sold to Amazon and Zhang, and they send a message right to your house.
Yep.
Yeah, I think it's also kind of cool. Like we could also think about doing some kind of study where you compare, like, I don't know if physicians would be down for this, but like how those results from like this classifier would compare to physician diagnoses and see like how well those align up. Because I guess, ultimately those might be cool things to compare and see like what gives the most accurate diagnosis results. Maybe like a combination of the two might be the best choice or something.
Right. That's a great point.
Well, great job.
Awesome.
Well done.
So, who else is on? Right. So I guess the last few are actually virtual, like demos that are recorded. So yeah, I'll just share it, and there's only like 2, I think. So I can let me share my screen. All right, so can you guys see my screen? I assume so. I'm just gonna play. I guess they all are muted. I guess you guys can. If you can't, just message me. I think it's fine. And then I think I have to like look in the Google Drive where all these are. All right. So yeah, so the last two are virtual videos that were pre-recorded. So I'm going to play those for anyone that wants to join in and listen.
People that are watching, you can see this, right?
I guess they're all muted, so I don't know.
Yeah, I can see it.
Okay, cool.
Okay, so we're going to play it. So the first one is going to be, I guess Alyssa Naritoku. No, sorry, I'm really bad with names. Alyssa's awesome, but I mispronounced her last name. Alyssa Naritoku, I guess. Is that better? I'm like terrible, Alyssa.
Just play the damn thing.
So you're gonna. It's fine. I'm gonna play it, but she's doing Graves' disease. She's doing Graves' disease.
There it is. Naritoku.
You got it.
The demographics are skewed, with women being 7 to 8 times as likely to have Graves than men. Symptoms are often hard to pinpoint for Graves' disease, and as a result, it can take more than a year for the patient to actually begin taking treatment. Furthermore, patients can be misdiagnosed for an estimated 6 months with diagnoses like depression or anxiety. This can be frustrating since patients are taking drugs that are ineffective and could be causing unnecessary side effects. Finally, the cost of diagnosis for Graves' disease, including the misdiagnosis, can be up to $100. The goal for this demo was to be able to differentiate a person with Graves' disease from a person without. Graves' disease has not been studied as an indication of NeuroLex previously, so I wanted to collect YouTube data for voice analysis. So with some assistance from Jim, I found 31 YouTube videos with 20-second clips for women for the control group and for women with Graves' disease. I separated women from men since there's such a big difference in the demographics for Graves. No creative bias, but hopefully in order to generate a more accurate diagnosis rate for Graves' disease, considering each population. I didn't complete finding the male Graves' disease population, but I'll elaborate on that in the next slide. I wasn't able to complete a model for voice analysis because of my course load and work schedule this past semester. However, Wendy and Nguyen was in the news for having Graves' disease. This was a great opportunity for doing a longitudinal study because she has over 4,000 videos on her YouTube channel. She was a radiologist for many years, and old audio files can also be found on YouTube. Because of this, I wanted to focus my efforts on finding videos to develop the female Graves' disease model rather than males. The next step would be to apply the female Graves' disease model, that's working, to these different clips from Wendy Williams and determine efficacy. So there were a few lessons learned from this project. The first one was that finding Graves' disease videos can be hard because Graves' disease has a smaller population group than other indications. And additionally, sometimes the individuals were in remission already, and I wanted to find individuals who were recently diagnosed. So what I did was I created a genome specifically for NeuroLex to use to find Graves' disease videos. And this worked out, as you can see on a screenshot, because I was able to access videos with military accounts that weren't as popular that were Graves' disease videos. Secondly, I learned that Graves' disease could have vocal features that could be used in a model in the future. So either audible tremor for singers and voice users, something that they can hear. And then nervousness in the voice. These are features that possibly could be used in higher evidence. The demo has the following impacts. If the next steps of modeling are successful, we will have a way to distinguish a person with Graves' disease from a person without Graves' disease. Therefore, it would reduce the time it would take to diagnose a person with Graves' disease. And by reducing the time it takes, it reduces the toll Graves' disease could have on a relationship, like one's family. This reduces the frustration the patient has from not knowing what's wrong with them or being misdiagnosed and what they perceive as treatment not really working. This will also save the patient money from having to get many tests per day. And furthermore, it will allow NeuroLex to write a relevant article about my fetal lines and for publicity if executed in the next few months. My vision for the project will be to continue. It has taught me a lot about developing my own research project and has allowed me to apply a lot of different classes to this project. Also, as a person affected by Graves' disease and someone who spent a lot of time misdiagnosed, and I'm sure what was happening to my body, I would like to see this demo in my be modeled. The first next step would be to create a model of Parkinson. Then it would be tested on multi-million audio for a longitudinal study. My next steps is that I will start my internship at Wagner Center, and I will finish my master's in the next year. Of course, I would like to stay involved and extend the scope of my project here at NeuroLex, and I would also be up to mentoring future innovation fellows and would love to go to future NeuroLex social events. So that's all for my presentation. Thank you for listening. Thank you, Adrian, for this opportunity to be a part two, and thank you, Reza, for being my mentor.
Awesome. Thanks, Alyssa. Virtually.
Thanks.
Very good video. Very good video. All right. So the last presentation.
That was genius about that.
Yeah. Just a very quick comment. I guess we'll leave comments for you if you ever watch this. I think we really like the idea of using a Gmail account to recommend videos. We think that's like an amazing idea to use their algorithms to select videos because they're the best algorithms. So we're definitely going to look at that a little deeper next time. For every tribe member, you created a supplemental account, which is kind of cool. All right, so I guess there's one last one, and I'm glad that you guys had the option to choose virtual because some of these they couldn't do in person because they had commitments today. So I think it worked out well. Yeah. So this is a folder. All right. So I'll give a quick brief. Mugdha is at.
Just give me a quick context of it.
So I'll just play it. Good point. I'll just play it. Reza's trolling me, so it's fine.
Sorry. Who's a controller?
The problem that the sun actually mentioned was anxiety. And during my research, I found that anxiety is a very prevalent mental illness, and it affects approximately 80% of the US population over the age of 18. Along with being one of the most common mental illnesses facing adults, anxiety disorder is highly treatable. But due to a multitude of reasons, only 36.9% of people diagnosed actually reach the treatment. For those who do receive treatment, the price tag isn't really affordable. It costs more than $6,000 annually for an individual diagnosed with any type of anxiety disorder. Additionally, anxiety disorder is commonly seen in individuals with pre-existing disorders. 50% of people diagnosed with depression are also diagnosed with anxiety disorder, leading to additional costs and more stress on the individual. Due to the choice of a variety of other disorders, anxiety disorder has also been a factor in increasing the hospitalization rates of those afflicted with mental illness. In a study done by the Mental Health Research Network, a 30-day all-cause readmission was 32% higher in those who were diagnosed with any sort of mental illness and anxiety, and 7.2% of these individuals were specifically diagnosed with anxiety. Due to the aforementioned reasons, there is a really clear need to better diagnose and target patients with anxiety disorders, especially for those who cannot really afford that high cost and those who are at high risk for other mental illness. So the goals for my demo was to basically create a new accurate method to diagnose anxiety anxiety disorder through the same type of audio input that NeuroLex is using. So my goal is to develop a set of cues to use as markers for audio testing that clinics and other places can use to test anxiety patients, and that would help diagnose them quicker and more specifically. As we use processes like machine learning, such as TensorFlow, which already exists, and other models to help mark different traits in speech that would lead to diagnosis of anxiety. So the solution that I came up with was create a large sample test and have different controls that would vary the results, and that would basically create a new model for diagnosing anxiety according to specific cues. So the solution that I came up with for my problem and the approach that I used to take it was to collect data. So in order to collect this data, I used YouTube of people who had already published anxiety stories online and national databases that all had anonymous audio files of people who had anxiety. And then used an audio trimmer to separate their speeches and make sure that each sample used had an equivalent amount of time and the equivalent amount of speech involved. I also made sure to restrict the age range to target people that were above the age of 18, like my research in the future. In order to analyze the data, I looked for filler words, inconsistencies, stuttering, and used the uses of the words and between them. So through the samples that I collected and the models that I put the audio data through, I collected more than 30 samples that had a 70% anxiety accuracy and a 78% depression accuracy. So some explanations for the accuracies could be that I need a larger sample size to get a greater accuracy. Also for the YouTube videos, I use both self-diagnosed and clinically diagnosed patients, and those patients could have different audio cues that would indicate your self-diagnosed versus a clinically diagnosed patient that kind of has a more specific prognosis. And the age range I use was 18 to about the age of 40. The potential impact for creating more specific anxiety tests is it can lower the annual death of patients not only with anxiety disorder, but people that face other disorders. Patients will spend more time in clinic, it will decrease the readmission rate, and it can potentially decrease the onset of other mental disorders if anxiety were to be treated earlier on. Anxiety is often a common link between other disorders and actually works as a precursor to the development of more significant mental disorders. Now, my personal treatment goals were to get an internship for the summer and apply to get a position in grad school after my undergraduate. I want to continue my studying biomedical engineering or get an MBA in the future. I would like to start my own company or get involved in a startup, but basically wherever the future takes me, I'm willing to go. And I do look forward to measuring future innovation knowledge and going to NeuroLex, but I got NeuroLex was really invaluable, and I really learned a lot about self-pacing and working toward a project that I was really passionate about. So, for my conclusion, I just basically decided that through the tests and the sample sizes and the results that I got, that there still needs to be a lot of testing done to more specify the type of test that needs to be done for anxiety. So, depending on general anxiety disorder or more specific anxiety disorders, different audio cues are seen to be more relevant depending on the category of anxiety. And therefore, I feel like more tests are needed to create not just one test for anxiety disorder, but multiple tests for more specific anxiety disorders. And this will be really helpful because it's really pertinent to other mental illnesses and it's prevalent in the US population. So not only will it help those that are just affected by anxiety, but it will affect those that are affected by more serious mental disorders like depression or schizophrenia. So finally, I would just like to say thank you for the opportunity of working with NeuroLex. I really enjoyed working with the company and learning a lot about my mentors and Zhang, and being able to get connected with a big community of people across the nation that are really passionate for working through a similar goal. And I look forward to hopefully working with you guys in the future and keeping in contact with the NeuroLex tribe. Thank you so much.
Awesome. Thank you so much as well. Let's give her a hand. Oh, she's not here. All right, so we're going to deliberate. We're going to probably close down the Zoom meeting. The next step is for us to sort of deliberate and judge all the demos. And we'll announce the winner on Zoom. Or sorry, a winner on Slack. I meant to say Slack. If you guys have any questions at all about how we judged your demos or any questions about anything else, please reach out to me afterwards, after Slack or whatever. I'm happy to talk through it. And we'd all, like that, I wanted to thank you all for really putting in the work this time around and really doing great demos. Each of you have done amazing work, and I hope you guys can take that with you wherever you go, and love to continue working with you all. It's been such a fun journey, this company with our core team and with you guys. You're just as much a part of our company as everyone here. So thank you so much. If you guys, like I said, we'll take about an hour, get through it, and let you guys know about 2:30, 3 p.m.-ish, the winner. So awesome, guys. Have a great rest of the weekend.